types of AC power systems: single-phase systems and three-phase systems. In this segment, we're going to introduce some terms that are associated with single-phase and three-phase systems so that you'll be familiar with them. You'll get a lot more detail when you learn about transformers, motors, and generators. Let's begin with the difference between a single-phase system and a three-phase system. Here's a very simple 110-volt single-phase system. It consists of two wires, a voltage source, and a resistor, which is the load. This is a simple 440-volt three-phase system. It has three wires, a voltage source, indicated by the three coils in this circle, and a load, indicated by these three resistors. Now that you've seen the difference between the two types of systems, let's look briefly at how they're used. First, we'll look at how a typical 110, 220-volt single-phase system is used in your plant or in your home. This type of system is a three-wire system. In a two-wire system like this one, the voltage supplied can only have one value. Since it is often desirable to have more than one voltage for plant and home applications, the three-wire single-phase system was invented. The three-wire system makes it possible to have two different voltages from one voltage source. The component that changes a two-wire single-phase system to a three-wire single-phase system is a transformer. As you see in this diagram, two lines come into the primary side of the transformer and three lines come off of the secondary side. The middle line on the secondary side is called the neutral line. It divides the secondary into two halves. The voltage between the neutral line and either the top line or the bottom line is 110 volts. So, with only three wires, we now have two 110-volt supplies. There's something else we can do with these three wires, though. We can use the two outside lines to get 220 volts. Thus, the three wires give us the 110, 220-volt system that is most useful for home and plant applications. Before we leave this diagram, I want to mention one more thing about the neutral line. In most systems, the neutral line is grounded as a protective measure. With the neutral line permanently grounded, if one of the other two lines accidentally becomes grounded, a short circuit will occur, and the circuit's fuses or circuit breakers will open the circuit. So, having the neutral line grounded allows you to know right away whenever a ground occurs. That's important because when you're connecting wires to lights and plugs, you don't want the top or bottom wire connected to ground, and you don't want the top and bottom wires connected together. Either of these connections would cause a short, and you could be shocked. By the way, one leg of a two-wire system is usually grounded for protective reasons too. Well, as I said, you'll be learning more about AC power systems as you move along in your training. So that's all we're going to say about single-phase systems at this point. Let's go on to three-phase systems. Three-phase AC systems are used most often when large amounts of electric power are required. That means you'll find these systems in most industrial installations. Let's take just a minute to look at the connections you'll find in three-phase systems. In this drawing, the three coils represent a three-phase transformer. As you can see, the two ends of each coil are connected to the ends of the other two. This kind of connection is called a delta connection. There are three wires coming out of the transformer. In this representation, the three wires are connected to three resistors. The resistors are connected together in a delta connection. Now, very briefly, we're going to look at the voltages and currents that are in the wires, the coils, and the resistors. As we'll see, the current and voltage in the coils and the resistors are not always the same as the current and voltage in the wires. The current that flows through the coils or the resistors is called phase current. The voltage that applied across the resistors or induced into the coils is called phase voltage. The current that flows through the wires is called line current, and the voltage that's applied to the wires is called line voltage. In this delta-connected system, the phase voltage equals the line voltage. Each coil is connected across two wires, so the voltage in each coil is equal to the voltage in those wires. This isn't true for current. The ends of two coils are connected to one wire, so the currents add together to form line current. The line current is equal to the square root of 3 times the phase current. In simpler terms, phase current times 1.73 equals the line current. You'll need to know this when you're taking readings of current and voltage on three-phase delta-connected systems. The reason for this relationship is that the phase currents add together to form the line current. Not all three-phase systems are delta-connected. Many three-phase systems use this type of connection, a Y or star connection. In a Y connection, one end of each coil or resistor is connected to one end of both of the other coils or resistors. The free ends of the coils and the resistors are connected to the three phase lines. Y connections have different effects on voltage and current than delta connections. In a Y-connected system, the phase current is equal to the line current. Because the current flowing in each line has to flow through the coil or resistor, the current can't split or add together the way it does in a delta connection. The phase voltage is not equal to the line voltage. Because the voltages in each coil or resistor have to be added with the voltage in one of the other coils or resistors to form the voltage across any two wires. In mathematical terms, phase voltage times 1.73 equals line voltage. As you can see from the differences between delta connections and Y connections, you need to know which type of system you're dealing with before you can take meaningful current and voltage readings. Your text includes diagrams of delta connections and Y connections and summarizes the voltage and current relationships for each type of system. Read through the last section in your text. Make sure you understand what we've covered about single-phase and three-phase systems. If you have any questions about them or about any of the other concepts we've discussed in this unit, ask your instructor about them.